Hi, good day to you and welcome to my channel that I tutor you in science for free. The topic in this video will be electromagnetic induction. In this chapter, we'll be talking about how the use of a force together with the help of magnets will produce an electric current. So in the previous chapter, explored DC circuits whereby we use magnets and a current whereby it comes directly from a battery to produce a force. So that is for DC circuits. In this chapter, we are talking about the reverse direction using force to generate electricity. So not going into great detail about this person called Michael Faraday who discovered this phenomenon whereby in an experiment of a coil, a solenoid, you push a magnet through the coil, you will get a reading on a galvanometer. And this process is called the electromagnetic induction process, where an induced electromotive force is produced in a conductor due to changing magnetic field. There is now a force used to push the electron around the circuit. And through these observations, there are certain findings. This Faraday's law of electromagnetic induction states that the magnitude of the induced EMF in a circuit is directly proportional to the rate of change of magnetic flux in the circuit. Okay, what is magnetic flux? Magnetic flux is the magnetic field in a given area, and I understand that this is a lot to take in. So generally what it means is, in this diagram, you push the magnet in faster, the needle is going to be deflected more. And that's it. If the magnet is stationary in the solenoid, there's no rate of change, so it's stationary. The needle of the galvanometer is not going to be deflected, it's going to be stationary. However, if you pull it out quickly, it's going to be deflected a lot. If you pull it out slowly, it's going to be deflected a little bit. So it's like a feedback system, it's like a response system that tells you how fast the magnet is going into or out of the solenoid. And if you have the opportunity to actually play with this setup live, you will experience a resistance. And that brings us to the next law called Lenz's law. It says that the direction of the induced EMF and hence the induced current in the closed circuit is always such that its magnetic effect opposes the motion or change producing it. Okay, so it's a lot of words again, right? So what it means is if you push the magnet through the solenoid will become and be induced to be a magnet to oppose the magnet. So if in this diagram, the north pole is entering, the solenoid will become a north pole at the entrance. It's trying to resist the magnet coming inwards. So if you are trying to pull the magnet out, then the exit will become a south pole because it's trying to attract back the magnet. So it's opposing the magnet leaving the solenoid. So with this topic, we have already touched on how magnetism, how a force, and how electricity all come together and work. And that brings us to this topic of the Fleming's right-hand rule. In the previous topic of the DC circuits, we are talking about the left-hand rule. So do not confuse with this chapter. In this chapter, we are talking about the right-hand rule, whereby it's talking about motion to electricity. And same, thumb, index finger, and middle finger are in 90 degrees to one another. Thumb being the force, index finger being the field, and middle finger being the current. So in this setup, it's a very simple generator whereby the force is generated through turning the handle, and thereby AD of the coil is going upwards and BC of the coil is going downwards. And same, slip rings. Slip rings allow the axle to turn while still maintaining contact, yet it's not attached dead to the axle, allowing it to move. And as the handle turns, a physical force is being applied, and through the influence of the magnet, an electric current is being produced to light up the bulb. Due to the rotation, current flows through the rectangular coil. And in this diagram, using your right hand rule, you can see that because AD is moving upwards and north to south points here, the current flows from A to D. And because BC is going downwards and north-south points this way, then the current flows from C to B. And this direction continues even though the coil has been flipped. Thereby, it's called an alternating current. So earlier, A current goes from A to D, and if A to D is flipped to the other side, now current is flowing from D to A. That is why it's called alternating current. AC, as known like AC generators or alternators. So in this diagram, you can see comparing to DC, direct current, AC uses slip rings and DC does not. This allows the coil not to get twisted, also providing electric contact. And this phenomenon can be plotted onto a graph over time, how the movement of the coil is turning. So at position 1, the rate of AD cutting the magnetic field lines is the largest, is moving the fastest. Therefore, it produces the greatest EMF reading. And at vertical position, there's no cutting of the magnetic field lines. Therefore, it's at 0. There is no EMF produced. And on the opposite side, it's also cutting at its greatest, but in the opposite direction. Therefore, it has the greatest negative EMF. And back to vertical, now at the bottom, it is not cutting any field lines, therefore reading is at 0. And the cycle continues. We call this the sinusoidal waveform. It's like a sine wave you learn in your mathematics. When the coil is rotated through one complete revolution, induced EMF also completes one cycle. One full round of positive cycle and a negative cycle. So similarly, the time taken for one complete cycle is called a period. The number of revolutions it makes in 1 second is called the frequency. And similarly, if you want to increase the power, the amount of voltage, you can increase the number of turns the coil has. If you double the amount of coils and you turn it the same speed, then the amount of EMF generated will be twice at the positive and twice at the negative. And if you spin it faster, then the rate of change is greater, right? If you spin it twice as fast, then the rate of change is greater. The produced EMF is twice the amount at the positive side, twice the amount at the negative side. And also, because it's spun faster, twice as fast, there's going to be two complete wave cycles in the same period of time as compared to the original speed. So this is something to take note. Increase in height as also increase in the number of complete cycles. And with this information, we go to the next topic. We will be talking about a transformer, not the one you see in the movies, but it's a device that changes a high alternating voltage to a low alternating voltage, or vice versa. So if it is from a large voltage to a small voltage, you call it a step down. If it's small voltage to a larger voltage, you call it a step up transformer. So this is how a basic transformer looks like. It has a soft iron core and it's a primary coil to the alternating current and a secondary coil towards the output that you want, say in a household appliance. And having the coil around the soft iron core magnetizes the iron, and it therefore passes the magnetism onto the secondary coil, causing it to have an induced current that goes out of the secondary coil. And soft iron is used because it is easily magnetized and demagnetized, so that to produce very efficient change of magnetic direction so that the secondary coil can catch on to the induced currents. Soft iron core also concentrate magnetic field lines, improving the link between primary and secondary coils. A very simple comparison over here, if you have a different number of turns in your primary coil as compared to your secondary coil, the effect is going to be different. So if you want to do a step up, you have less coil in primary, more coil in secondary. Or step down, more coil in primary and less coil in secondary. How are you going to effectively create the output that you want? Over here, it can be easily calculated. The voltage of the primary versus the voltage of the secondary, number of turns of primary, number of turns of secondary. And this formula can be rotated as long as the primary and secondary, they are in the same category. As long as they are not diagonal, you will be fine. So these are very simple formulas to abide by. And a question will usually give you 3 of them and you have to find out the last one. Same with this formula. Power conversion, so power of the primary, power of the secondary, so P equals to VI, right? And same question will give you, there are 4 variables here. The question will give you 3 of them, you have to find out the last one. And usually transformers are not able to transfer all the energy from the primary coil to the secondary coil, and there are some wastage of powers. The transfer of power from the primary coil to the secondary coil is not fully efficient, and therefore we can calculate the efficiency by this formula, output over input times 100. And over here in the VI formula, why we can do this is because laws of conservation of energy applies. Energy is not created, therefore energy is all just transferred. And that power is also transferred. It's just from the primary side to the secondary side. And with that, we will go through some questions. It's a pretty short chapter, but a lot of applications are involved. Okay, a small vertical coil connected to a sensitive emitter. Okay, magnet falls into the coil. Emitter turns to the right. How does the emitter move as the magnet falls away from the coil? So now it's entering, it turns to the right. As it falls away from the coil, it's going to resist, right? It's trying to attract the magnet back into the coil. So right side is resist. It should go to the left because it's trying to attract back. So it moves quickly to the left of the 0 position, then returns to 0 because it has fully fallen through. The answer will be this. This is a simple transformer, more turns on secondary coil than primary coil. Which statement is correct? The answer will be this one. Alternating current in the primary coil gives rise to the voltage of the secondary coil. Student pushes north pole into Q of a solenoid. Deflection to the right. What produces a deflection of the same direction? So you just have to reverse everything, right? If you push it in using the north pole, Q will be a north pole, right? And if you want that part to be a north pole, you have to pull south pole out of P, or rather pushing south pole into the end of P. Two leads emerging from a box are connected to a sensitive emitter. When bar magnet moves toward the open end of the box, emitter deflects right. Bar magnet stops, needle returns to 0. What is connected to the two leads inside the box? This is pretty simple. It should just be a coil. Therefore, the circuit is able to receive the induced current. Electromagnetic induction can be demonstrated using these items. In the space below, draw these apparatus out. Drawing of circuits is also a skill in physics, so this is how it's supposed to look like. Describe how the apparatus is used to produce an induced current. So therefore, when a bar magnet is pushed into the coil, quickly induced current is produced. Okay, why? When it's pushed quickly, change in magnetic linkage between bar, magnet and coil of wire due to Faraday's law, an induced current is being produced, causing an induced current to flow such that it creates an induced magnet to oppose this change. Graph shows an output of AC generator. Generator rotates 20 times in 1 second. How do you draw a graph that shows coil rotating 10 times in 1 second? Therefore, you need to lower the height and also extend the period, right? So it's going to take twice as long and half the height. Okay, this is quite simple. An output voltage produced in the coil below, one side is P. When is the output voltage 0? So output voltage 0 will be where the magnetic field lines are not being cut. Therefore, it must be only in the vertical position, either at the top or the bottom. So next, why is high voltage used to transmit electrical energy along cables from power station? This is done because less thermal energy is lost or produced in the cables. This is a unique AC generator where the magnet rotates. Okay, transformer, 200 turns primary, 50 turns secondary. What is the current in the primary coil? So using this formula, you plonk the three values you have inside: 200 turns, 50 turns, 240 volt, and the last volt you do not know. The secondary voltage will be 60 volt. Then current in the secondary coil will be V equals to IR formula. You get 3 amperes, and then you plunk it back into this formula, IV, you'll get this. So this is pretty challenging. As a multiple choice question, you need 3 formulas to help you get the answer. Okay, long transmission line, 230 volts, 2 houses. Heaters are switched on. House X switches off the heaters in his house. What happens in house Y? This will be the answer. There will be rise in voltage supplied and in the power used. So this is very interesting. That's why I chose it for discussion today. So looking at this in such a manner, you can redraw it as a circuit. Long transmission line means it's just a resistor. And heaters are generally also resistors, right? So if you simplify it, you'll get a smaller resistance as compared to X and Y on their own. Recall this 1 over R formula. And then if one of them is switched off, then the circuit will look like that. And then if Y, larger resistance than combined resistance, the potential difference, the voltage is larger as well. So calculating power, you get V squared over R. And if voltage increases, Therefore, power also increases. So this is also yet another one of the more challenging questions. Ideal transformer with this setup is shown. What are the possible readings for voltmeter and ammeter of the output circuit? So P equals to VI, this times this, 144 volt. And the only combination would be this, 360 volt and 0.48. Okay, varying potential difference is connected across a 50 ohm resistor in a cathode ray oscilloscope. So CRO is just a screen that shows you some readings. Resistor and CRO connected in parallel. So this is the waveform shown. Y gain is 10 volt per division and the time is 0.25 millisecond per division. What is the energy dissipated in one period? So one period is just a sine wave, so it's a one up, one down, one S shape. Time taken is 2 units. Then the amplitude is 20 volt because there are 2 divisions. So the energy is E equals to PT, or rather V square RT, and you plonk in all the values and you will get this value. So you can see in physics, formula is very important. And last question, very long question indeed. It's a free response question. A transformer is shown, alternating current 230 volt. So describe what is alternating voltage. Alternating voltage generally has this description. I won't go too much into detail. So state how magnetic field in the iron core induces a voltage in the secondary coil. So because there's alternating voltage, there will be alternating current and changing magnetic field around the primary coil. This is concentrated into the iron core. The change in the flux linkage produces the voltage due to Faraday's law. Purpose of the iron core is to improve and concentrate the magnetic field lines between the primary and secondary coil. So it's stated that 480 turns on primary coil. So what's the smallest number to give at least 8 volt of the secondary coil? So this is what you want, right? So throw formula, put in all the values, you will get this number. So the minimum number to hit at least 8 volt will be a rounded out number at 17. Student determines input and output power to calculate efficiency. Voltmeters and ammeters are being used. Draw 2 voltmeters and 2 ammeters to calculate the efficiency. This is how it's drawn. Voltmeter must always be connected in parallel. Ammeter must always be connected in series. State what is meant by efficiency. Efficiency is just this. Current into primary coil is this. Current into secondary coil is this. And output voltage is this. Calculate the efficiency. So power in primary coil is this, P equals to VI, and in secondary coil, P equals to VI is this. Therefore, small over big times 100, you will get your answer. Or rather, output over input times 100, you will get your efficiency. And that is all for today. Hope you enjoyed this video. Do give it a like and subscribe, and share it with somebody who needs to see this. And I will catch you in the next video. Bye!